Greetings, class! Why do the soft, highly reactive metal sodium, which, practically explodes when it touches water, and the toxic green gas chlorine, which is literally deadly to inhale, combine to form the perfectly safe table salt we eat every single day? I mean, it's a staggering scientific mystery, right? How on earth can two inherently dangerous elements react to create something absolutely essential to human life? Well, the answer doesn't lie in magic or alchemy, but in the precise mathematical exchange of subatomic particles. Today, we will study ionic bonding.
Okay, let's dive right into the absolute foundation of everything we're going to cover in this explainer. On this slide, we have our core definition. Ionic bonding is the complete, absolute transfer of one or more electrons from a metal atom to a nonmetal atom. Actually, scratch the word sharing from your brain right now. This is a full-on handover. By transferring these negatively charged electrons, we create oppositely charged particles, which we call ions. And since opposites attract, these ions are held together by a tremendously powerful electrostatic attraction. Now, sometimes you'll hear this called an electrovalent bond. That's a great term because it hits the nail on the head regarding the pure electrical nature of this bond. Keep this definition locked in your memory because it literally dictates every single property we're about to explore.
Here are the core details regarding this topic. Review them intently for their being crucial for your finals.
Moving on, how do we actually form these charged particles? Let's look at the positive side of things. Cations. You can always remember them with a terribly cheesy but super effective memory trick. Cations are positive, like a cat. Remember, neutral atoms only become charged by moving electrons around, never protons. Metal atoms are your classic electron losers. So, when a metal like sodium loses an electron, suddenly it has 11 positive protons but only 10 negative electrons. The math is simple, right? It leaves a net positive charge of 1. The magnitude of that charge perfectly mirrors the exact number of electrons lost. If an atom loses 2 outer electrons like magnesium or calcium, you get a positive 2 charge, which we write as Mg2+ or Ca2+. They literally give away their negative baggage to become positively charged. Kind of a nice life lesson, actually. Of course, those ejected electrons have to go somewhere, right? Enter the nonmetals. These guys act as our electron gainers. When they take on extra electrons, they form negative ions, which are known as anions. A good way to remember this, think of an anion as an A-negative ion. Because they're gaining those negatively charged electrons, their total electron count shoots up past their proton count. Take chlorine, for example. It starts out totally neutral with 17 protons and 17 electrons. But when it aggressively grabs one extra electron from a metal, it becomes the chloride ion, Cl-, with a -1 charge. Oxygen? Well, it needs 2 electrons, so it forms the oxide ion, O2-. Basically, the exact number of electrons gained rigidly dictates that final negative charge.
These are the vital facts linked to this section. Study them thoroughly as they are vital for examination point of view.
So you might be wondering, why does this happen at all? Atoms don't just throw electrons around for fun. They're driven by an ultimate quest for stability. And in the atomic world, stability means joining the highly exclusive noble gas VIP club. Noble gases, like neon and argon in group 0, are chemically elite because their outer electron shells are completely full. They're totally unreactive. This brings us to the octet rule. Atoms will ruthlessly transfer electrons until they achieve that perfect set of 8 outer electrons. For instance, Na+, Mg2+, and O2- all achieve the exact same 2,8 electronic configuration as neon. They're completely different elements, sure, but chemically speaking, they've achieved that stable, noble gas perfection. To actually visualize this invisible subatomic swap, we use dot and cross diagrams. And listen up, because for your exams, you absolutely must follow these strict rules. First, draw only the outer electron shells. Drawing the inner shells is just a waste of time and needlessly clutters the whole thing. We use dots for one atom's electrons and crosses for the others. But here's a vital scientific secret. In reality, all electrons are physically identical. There's no such thing as a cross electron. We just use different symbols to keep track of the accounting. Second rule, enclose your final ions entirely in square brackets to show the charges evenly distributed. Third, put the exact charge right up at the top right-hand corner. Fourth, your metal cation gets an empty shell with its chemical symbol inside. And finally, your non-metal anion must show a full shell of 8, displaying its original crosses plus the newly acquired dots from the metal.
These are the key points related to this topic. Focus on them carefully as they are considered essential for your exams.
Let's look at a worked example that brilliantly illustrates this classic one-to-one transfer. Sodium chloride. Sodium, a group 1 metal, has a single outer electron hanging on, giving it a configuration of 2, 8, 1. Chlorine, over in group 7, has 7 outer electrons. It desperately needs just one more to reach that magic number 8. It's literally a match made in chemical heaven. Sodium completely transfers its lone outer electron directly to chlorine. Sodium drops down to a stable 2, 8, becoming Na+. Chlorine fills up to 2, 8, 8, becoming Cl-. Because the +1 and -1 charges perfectly cancel out to 0, our final formula is simply NaCl. It's a perfectly balanced, electrically neutral relationship driven entirely by strong electrostatic attraction. Okay, let's level up. What happens when we need to transfer multiple electrons? Consider magnesium oxide. Magnesium is a group 2 metal, meaning it carries 2 outer electrons. Oxygen is group 6, so it has 6 outer electrons and needs exactly 2 to complete its octet. So instead of a single electron jumping ship, both of magnesium's outer electrons are transferred to a single oxygen atom. Magnesium becomes Mg2+, and oxygen becomes O2-. Once again, look at how perfectly they cancel out. A +2 and a -2 equal absolute 0, which maintains that beautiful one-to-one atomic ratio in the final formula, MgO. It's just elegant, mathematically satisfying chemistry. But what if the math doesn't align quite so easily? Take calcium chloride, for example. Calcium is in group 2. It absolutely must lose 2 electrons for stability. However, chlorine is in group 7 and can only accept 1 electron per atom before its shell is completely full. Chlorine's VIP club is strictly at capacity. So what does calcium do? It simply invites a second chlorine atom to the party. 1 electron goes to the first chlorine atom, and the second electron goes to the second chlorine atom. We end up with 1 Ca2+ ion and 2 separate Cl- ions. So the formula becomes CaCl2, perfectly balancing a +2 charge with 2 -1 charges. It's a slightly more complex ratio, but it achieves a perfectly simple objective: overall electrical neutrality.
Now, let's zoom out and see how this builds into the physical world. You see, you don't just get one single sodium ion bonding to one single chloride ion. That's not how it works. In reality, billions of these positive and negative ions arrange themselves into a giant, macroscopic, three-dimensional structure known as an ionic crystal lattice. Every single positive ion is entirely surrounded by multiple negative ions, and vice versa. In sodium chloride, they form what we call a face-centered cubic structure, meaning each sodium is locked in by 6 chlorides and each chloride by 6 sodiums. This isn't just random chaos. It's a highly ordered, geometric, repeating pattern extending in all 3 dimensions. And that is exactly why, when you look at a simple grain of salt under a microscope, you see perfect little cubes with flat faces and sharp, defined edges.
But as you'll see, not all ionic lattices are created equal. The overall bonding in this crystal lattice is a highly forceful network of electrostatic attractions. To deeply understand its strength, we have to talk about Coulomb's law. Coulomb's law essentially states that the force of attraction increases heavily as the ion charges increase, and it also increases as the distance between the ions decreases. Let's compare our previous examples. Mg2+ and O2- have double the charge of Na+ and Cl-. Because of those +2 and -2 charges, the magnetic pole is vastly stronger. Consequently, sodium chloride melts at around 800 degrees Celsius, but magnesium oxide, that requires a staggering 2,800 degrees Celsius to melt. Furthermore, smaller ions can pack much closer together, which just further increases that total electrostatic grip across the lattice. Because of this giant lattice structure, ionic compounds share a very specific profile of thermal and physical characteristics. First off, they have incredibly high melting and boiling points. Why? Because tearing apart billions of strong electrostatic bonds throughout that massive lattice requires a massive amount of thermal energy. At room temperature, they are totally solid, the ions are firmly locked in fixed positions. But interestingly, they are highly brittle. If you hit an ionic crystal with a physical force, it causes the layers of ions to shift. Suddenly, you have positive ions aligning right next to positive ions, and negative next to negative. The sheer electrostatic repulsion instantly shatters the entire crystal. It's a rather dramatic overreaction on an atomic scale, if you ask me. Finally, they're generally soluble in water. Polar water molecules basically act like tiny magnets, attracting and plucking ions right out of the lattice structure to pull them into solution. All right, let's talk about electrical conductivity, because this is a massive, high-yield topic that examiners absolutely love to test. Here's the golden rule. To conduct electricity, a substance absolutely must have freely moving charged particles. In the solid state, ionic compounds simply cannot conduct. The ions are locked in a rigid lattice prison and cannot move. No movement, no conductivity. However, if you apply intense heat and melt it into a molten state, or if you dissolve it in an aqueous solution, that lattice breaks apart. The ions are suddenly free to move around and carry an electrical charge. So remember this strict structural comparison. Solid means absolutely no conduction, molten or dissolved means full conduction.
Okay, let's bring it all home. Here is your rapid-fire masterclass summary of the absolute core concepts you need to lock in for your exams. Ionic bonds form via the complete, uncompromising transfer of electrons from metals to nonmetals. Metals lose electrons to become positive cations. Nonmetals gain them to become negative anions. The entire driving force behind this whole process is achieving that highly stable, full outer shell noble gas configuration. When you're drawing dot and cross diagrams, use square brackets, explicitly track your charges, and only draw those outer shells. Remember that these ions don't exist in microscopic isolation. They build massive, repeating 3D crystal lattices, and it's this incredibly strong electrostatic network that directly dictates their high melting points, their shattering brittleness, and their unique state-dependent electrical conductivity.
So, we've learned just how unfathomably strong these electrostatic bonds really are, which brings me to a fascinating scientific paradox to leave you with today. If ionic compounds like table salt are locked in a massive, rigid, brittle lattice that requires nearly 1,000 degrees of intense heat just to melt, how is it that a simple glass of water at room temperature can completely tear this massive structure apart in mere seconds? Think about the immense, unseen polar pulling power of those tiny water molecules the next time you dissolve salt in your kitchen. Class dismissed, and keep questioning the microscopic world around you.
Important terminology for this topic is shown on the screen, arranged according to various exam boards. These terms demand focused attention during revision as they are highly significant and must never be overlooked. Furthermore, a past paper evaluation is included for each board and paper format. Give this paper attention too, since it will strongly enhance and refine your preparation. Additionally, aims to grasp the meaning and usage of every term instead of rote learning them individually. Consistent practice of these terms in past paper questions will greatly boost your precision and overall exam results.
Please subscribe our channel to get more educational videos. Thank you.